Imagine two analysts run exact same experiment. First analyst collects 200 users and concludes feature works. Second analyst collects 20,000 users and concludes feature does not work. Same experiment, completely different conclusions. So who is right? Answer is maybe neither. Because before asking what does the data say, there is more important question. Did we collect enough data to trust the answer? And this is where many experiments quietly fail. Some experiments end too early. Some run far longer than necessary. Some waste months collecting data. Others make decisions using numbers that were never reliable in the first place. And behind all these mistakes lies one critical concept: sample size determination. Because statistics is not just about analyzing data, it is about knowing how much data is enough. Too little data, you risk making decisions based on randomness. Too much data, you waste time, money, and opportunity. The goal is finding point where evidence becomes reliable. And that is exactly what sample size determination helps us do. Welcome back to Shital's Data Desk. I'm Shital, and in this video, we will break down below topics one by one. By the end of this video, you will understand why deciding how much data to collect is one of the most important decisions in all of statistics. So, let's start with the basics. What exactly is sample size? Sample size simply means how many observations we need before making a decision. If we are running an A/B test, it means how many users should participate. If we are conducting a survey, it means how many people should be questioned. If we are studying patients in clinical trial, it means how many participants should be included. But here's something many beginners misunderstand. Sample size is not about collecting as much data as possible or collecting least amount of data possible either. It is about collecting enough information to separate signal from randomness. Because every data set contains randomness, and collecting too little data can lead us to unreliable conclusions. The goal of sample size determination is not perfection, but reliability. Because experiments are ultimately uncertainty reduction machines. But why do small samples behave so unpredictably? To understand that, we need to understand variability. Imagine flipping a coin only 5 times. Getting 4 heads doesn't mean coin is biased. That is simply luck. But if you flip the coin 10,000 times, proportion of heads starts moving closer and closer to 50%. Randomness begins averaging out. This idea is one of the most important principles in statistics. It is called law of large numbers. As sample size increases, averages converge towards truth. Small samples are unstable. Large samples are stable. And this instability affects everything: means, proportions, conversion rates, revenue, click through rates, retention, every metric. Small samples often produce dramatic looking effects that later disappear. Because randomness is powerful and sample size is ultimately our defense against being fooled by chance. But stability alone is not enough. We also want our estimates to be precise. Suppose we repeatedly run same experiment over and over again, will we get exactly same answer every time? No. Each sample will produce slightly different results. Some estimates will be higher, others lower, and that natural variation is measured by something called standard error. Standard error tells us how much our estimates fluctuate from sample to sample. Large standard error means high uncertainty. Small standard error means greater precision. And here's the key insight. As sample size increases, standard error decreases, which means our estimates become increasingly stable. This also affects something analysts use constantly: confidence intervals. Small samples create wide confidence intervals. Large samples create narrow confidence intervals. Because more data reduces uncertainty. So, sample size doesn't just affect whether we detect effects, it also affects how precisely we measure them. But even precise estimates can still lead us to wrong conclusion. When we run experiments, there are always two kinds of errors. The first is false positive, seeing an effect that doesn't actually exist, concluding this feature works when in reality it does not. Second error is false negative, missing an effect that really does exist, concluding nothing changed when in reality feature genuinely improved performance. In statistics, false positives are called type 1 errors, and the probability of making them is controlled by alpha. False negatives are called type 2 errors, and the probability of making them is controlled by beta, and sample size directly controls both. Too little data and false negatives become common. Randomness hides real effects. Too much data and experiments become costly and inefficient. So, sample size is really a balancing act between certainty, speed, cost, and risk. But what determines how much data we actually need? Suppose your website converts at 5%. Now imagine two possible improvements, 5% to 7% and 5% to 5.2%. Which improvement is easier to detect? Obviously, the larger one. Because large effects stand out clearly from noise. Small effects look almost identical to randomness. This is why effect size matters so much. And in experimentation, we often express it using MDE, that is, minimum detectable effect, the smallest improvement we care about finding. And here comes one of the most surprising truths in statistics. Reducing MDE slightly can explode sample size requirement because their relationship is not linear. Want to detect effects half as large? You may need 4 times more users, sometimes even more. Tiny effects demand extraordinary precision, and precision requires data. But effect size is not the only thing influencing sample size. So far, we have encountered 4 ingredients that determine sample size: effect size, variability, alpha, and statistical power. These requirements constantly pull against each other. And sample size is the number that satisfies all of those requirements simultaneously. Which means sample size is not something we simply guess. It is the number that satisfies all of these competing requirements. But how do statisticians combine all these ingredients into one answer? That's exactly what power analysis helps us do. Before collecting single observation, we need to answer an important question. How much data do we actually need? That is exactly what power analysis is designed to answer. Power analysis works backwards. Instead of asking, what can we detect? It asks, given the effect we care about and the certainty we want, how much data is necessary? To answer that question, power analysis combines 4 ingredients: effect size, variability, alpha, and statistical power. From those inputs, it calculates required sample size. In other words, sample size is not chosen, it is calculated. Power analysis acts like planning tool. Before spending money, launching experiments and exposing users, we first estimate what improvement matters. How much risk are we willing to accept and how sensitive should the experiment be? And based on those answers, power analysis tells us how many observations are necessary. That is why power analysis happens before experiments begin, not afterwards. But sample size is not just about statistics, it is also about business. More data sounds great, but data is not free. Large sample sizes means longer experiments, delayed decisions, engineering resources, opportunity cost, and slower learning. Startups often prefer speed, so they may accept larger MDEs and smaller samples. Big tech companies operate at enormous scale. Even tiny improvements can generate millions, so they willingly run massive experiments. Healthcare studies often require very large samples because even small improvements can have life saving consequences. Different industries make different choices because sample size is not really about maximizing data, it is about balancing speed, cost, and certainty. And that is where many analysts make mistakes. Mistake 1, choosing sample sizes randomly. 500 users, 1000 users, 10,000 users. Nice round numbers with no statistical justification. Mistake 2, stopping experiments early. Peeking at results every day and ending test the moment significance appears. This dramatically increases false positives. Mistake 3, underpowered experiments. Collecting too little data, missing real improvements, and sometimes teams do the opposite, collecting far more data than necessary, creating expensive and unnecessarily slow experiments. Mistake 4, sample ratio mismatch. When traffic allocation becomes uneven due to tracking or randomization errors. Even perfect statistical methods cannot fix biased data. Mistake 5, publication bias or replication crisis. Low powered studies often produce unstable and exaggerated findings, and many scientists believe this has contributed to the replication crisis, where published results fail to reproduce. And perhaps the biggest mistake of all, mistake 6, copying numbers from blog posts. Because sample size depends entirely on context. What works for Netflix may be completely wrong for your company. So, what should we remember from all of this? Sample size determination is not about guessing, and it is not about collecting infinite data. It is about finding amount of information necessary to make reliable decisions. Small samples create instability. Large samples create confidence. But larger samples also create cost. Effect size, variability, alpha, and power together determine how much data we need. Power analysis translates those requirements into sample size. And ultimately, sample size is where statistics, risk, cost, and business priorities all come together. Because experiments are not truth machines, they are detection systems. And even detection system has limits. Sample size determines how clearly your system can separate signal from noise. Too little data and reality remains hidden. Too much data and the cost becomes unnecessary. Which means great analysts don't ask how much data can we collect. They ask how much data do we actually need. Because good experimentation is not about maximizing data. It is about maximizing decisions. If you found this video helpful, don't forget to like, share and subscribe to Shital's Data Desk. Thanks for watching and I'll see you in next video.